So chapter 16 deals with random variables. Random variables are not like variables we solve for like we're used to in algebra. They are used to represent a specific outcome. We play the game called Greedy Pig. If you were in class, you know what that's about. So here's some vocabulary. A random variable assumes any of several different values as a result of some random event denoted with a capital letter. And it's not always X, Y, and Z. Sometimes we use letters that are very specific so that it makes sense. Like if we're talking about maintenance, we would use M. If we're talking about points, sometimes we want to use P. The problem with P is sometimes it gets confused with the probability. A random variable that is discrete takes one of finite numbers of distinct outcomes. If we're talking about Greedy Pig, we had distinct outcomes. You either got 1 point, 2 points, 3 points, 4 points, 0 points, or 6 points. A continuous random variable can take a range of values, and those are less commonly used in our class. A probability model is a function that associates the probability x with each value of a discrete random variable, capital X. So it's denoted P of x, capital X equals x. And so that basically means whatever your random variable is, in this case, if we talk about Greedy Pig, your points, what's the probability that your points are equal to 1? What's the probability that your points are equal to 2, or equal to 0, or equal to 6? And so we fill in this with the actual numbers that are possible for the little x, and the big X still represents our random variable, the points we've earned. The expected value is the theoretical long-run average value. It's the center of the model. We have two notations for that. Capital E of X, or whatever variable you're using for your random variable, or mu. It's the sum of the probability times the value. So the mu is equal to E of X. Okay, so when it's what's the expected value, or what do you expect on average, you're looking for mean. And that's the sum of the X values times the probabilities. And we're going to create a probability model to help this make more sense. But it's basically the number of points you can earn times the probability that you get those points. The standard deviation describes the spread of the model, just like our normal models. It's the square root of the variance. We use SD of X, or sigma. Sigma squared is variance. The variance is the sum of the X values. So for Greedy Pig, it would be the points we earn minus the average points we expect. And we square that. Remember, because the mean, if I subtract them all from the mean, I end up with 0, times the probability that you get that point value. And then to get the standard deviation, we take the square root of that answer. We're going to come back to creating a probability model for Greedy Pig and calculating that expected value later. Now, we need to understand how we can change by a constant, or how we can add together random variables. When we are adding a constant C, okay, it adds to our mean, it adds to our expected value. So for example, if I were to add 1 point to each roll of the die, so instead of getting a 1, you get a 2. When I roll a 2, you get 3 points. When I roll a 3, you get 4. When I roll a 4, you get 5. And when I roll a 6, you get 7. But you still get 0 points with a 5. That would, I'm adding 1 point to each of the values. That would actually just add 1 point to the average. And again, this was very similar to how we did means, medians, minimum, maximum, measures of position, and measure of spread back in chapter 6. When we added, it changed the mean, it changed the measures of position, but it didn't change the spread. So the variance doesn't change, and therefore the standard deviation doesn't change if I'm just adding a constant. Because you've just shifted it down the number line, you haven't changed how spread out it is. But if you multiply by a constant, it does change both the mean and the standard deviation. We can just multiply the mean by that number. Again, the same was true of measures of position in chapter 6. And then the standard deviation, we can multiply by that. Now, a lot of formulas only talk about the variance, but the variance squared, or the constant squared times the variance is the same as, if I take the square root of that, a times the standard deviation. So it does multiply to the standard deviation as well. And this makes it a lot easier to make changes because we don't have to recalculate all the probabilities in the probability model. Now, if I'm adding and subtracting independent random variables, the probability that the one random variable plus or minus the second random variable is the same as just adding the means or expected values or subtracting the expected values. If they're independent, then the variances add. The variances never subtract because it never becomes less variable when you're subtracting numbers. And so if I'm adding them, this variances add, which means the standard deviation is sigma squared. So if I want to change these all to standard deviation, I would make that sigma squared, sigma squared, sigma squared, and then I would have to take the square root in order to get standard deviation. So the standard deviation follows something similar to our Pythagorean theorem with sigma of x squared plus sigma y squared, all take the square root of that when I am adding or subtracting independent random variables. And notice that there isn't a plus and minus inside the square root because it is always going to add. Consider this game. Okay? No points if you roll a 1, a 2, or a 3, 5 points if you roll a 4 or a 5, and 50 points for a 6. We're going to use this game to create a probability model and then find the expected value and standard deviation and talk about the different concepts that we looked at in the vocabulary type section. So our probability model starts with x, or we could call it p for points. But x is the number of points we earned. So the possibilities for that in our probability model are 0 points, 5 points, and 50 points. And then the second row is the probability that your random variable, the points, is equal to the number above. So this first box is the probability that your points are 0. And since it's rolling a 1, a 2, or a 3, that's 3/6 or 1/2. Because the probability of getting no points is 3 out of the 6 faces of the die. Then for the rolling a 5, the probability is 2, because 4 and 5 are 2 out of the 6 faces of the die, and that reduces to 1/3. And then there's 1/6 chance, rolling a 6, of getting 50 points. So this is our probability model. Now, if I want to find the expected value, or the mean, the expected value is the sum of the x values times the probability. So that means 0, the x value, times the probability of 1/2, plus 5 times the probability of 1/3, plus 50 times the probability of 1/6. And so that's 0 plus 5/3 plus 56, which is 5/3 plus, we'll reduce 56 to 25/3, and that's 30/3, which is 10. So my expected value is 10 points. Now that's not an actual possibility, but what this means is if you played the game over and over and over again, an infinite number of times, you would average 10 points per play. Okay? That's what the expected value means. Now the standard deviation of x is the square root of the variance. And the variance of x, the variance of x is the x value minus the mean, the expected value, squared, times the probability. And it's the sum of all those. So we take our first x value 0, minus my expected value we got of 10. We square it, and we multiply it by the probability. And then we add it to the next one. 5 minus 10 squared times 1/3. And then 50 minus 10 squared times 1/6. So that's negative 10 squared 100 times 1/2, that's 50. And that's 5. Negative 5 squared is 25 times 1/3, so that's 25/3. And then that's 40 squared, which is 1600/6, which reduces to 800/3. And then I can add that up. That's 825/3 plus 50. 825 divided by 3 is 50 plus 2, 75. So that's 325. Now remember, we're taking the square root of this now because this is my variance. Okay, the variance is 325, and the standard deviation is the square root of the variance, and that is 18.03. So my standard deviation is 18.03. Now, so that's the first question. The second question is, imagine we doubled the points awarded. What are the new mean and the standard deviation? Well, when we were talking about the different formulas, we said that the mean and standard deviation are treated a lot or the same as we did in Chapter 6. So if we were multiplying, rescaling, we multiplied the mean and the standard deviation. And so that is true here because my new possibilities would be 0 points, 10 points, and 100 points. So I've just doubled all of the numbers, which is just going to double my mean. So my new mean, so 2 times x, the mean of 2 times the points is 2 times the expected value, so 2 times 10 is 20. Now if you made the probability model this new one, the probabilities would be the same, and you would end up with 20 if you recalculated that, because think about it, you're just multiplying the 5 and the 50 times 2, so that's going to end up just multiplying my final answer by 2. And the same is true for standard deviation. Remember, standard deviation rescales, but it doesn't translate. So I can't add to the standard deviation. It doesn't increase the spread. But when I multiply, it does increase how spread out they are. So my standard deviation of 2 times my random variable is 2 times my standard deviation. So that's 2 times 18.03, 32.06, 36.06. Sorry. So if I were to say add 5 points to it, and so instead of 0, it would be 5, 10, and 55, my standard deviation wouldn't change because all I did was move everything to the side, 5. It's still the same spread. And we could test this by actually creating the probability model and then redoing the calculation. And we'll talk in a little bit how to use the calculator to do the calculation. Now, the third here is imagine you played the game twice. What are the new mean and standard deviation for your total points? So if you're playing the game twice, okay, so the first roll and your second roll, you have the possibility of getting 0, 5, and 50 points on both rolls. So your points would be the sum. 0 plus 0 would be 0 points. 0 and 5, or 5 and 0 is 5 points. 50 and 0 is 50 points. And then your first roll is 0, your second roll is 5. That's 5 points. 5 for your first roll, 5 for your second roll would be 10. 5 and 50 is 55. And then we have 50, 55, and 100. So what I want you to see by writing out all these possibilities is that there's more variability in the possibilities. So our standard deviation does change, but it's not as simple as just adding the standard deviations together. Standard deviations do not add, the variances add. So I could create a probability model for this, but I don't really need to, because the idea that I'm playing the game twice, we said the expected value, if I am doing x1 and then x2, that's playing the game one time and then playing it again, is the expected value of the first play plus the expected value of the second play. I can add together my means and expected values, and that also gives us 20. And my standard deviations, though, we said the variances of x1 plus x2 adds. So that's the variance of x1 plus the variance of x2. That's playing the game the first time and playing the game the second time. So, but the variance is the standard deviation squared, right? So the standard deviation squared, because I don't have the variance number. Well, I actually have the 325, but that's 18.03 plus 18.03 squared. Those are both squared. That gives me the new variance, and then I have to take the square root of that to get the standard deviation. So the variances add, not the standard deviation. So we have to kind of use this Pythagorean theorem of statistics. And I get do it real quick in a calculator. 25.498 or 25.5 is the standard deviation of playing the game twice. Okay, so my new standard deviation is 25.5. Now the variances will always add whether or not we add or subtract the points, because we're going to get more spread out. And so I want to show you that next. The next one says, suppose you and a friend both play the dice game. What are the mean and standard deviation of the differences in your score? So now we're talking about how is it going to be different when I take your score minus your friend's roll. So here's you and your friend. Okay, and then we're going to subtract the numbers. So you still have a possibility of getting 0, 5, or 50 points, and your friend has a possibility of getting 0, 5, or 50 points. But now, instead of adding those points together, we're going to subtract them. And so 0, if you had a 0 and your friend had a 0, the difference in your points is 0. If you had a 5 and your friend had a 0, the difference in your points are 5. We're going to do you minus your friend. And then if you had 50, your friend had 0, then that's 50 if I subtract them. If you had a 0 and your friend had 5, now you're at negative 5 because you're doing you minus your friend. And then 5 minus 5 is 0, and 50 minus 5 is 45. And then 0 minus 50 is negative 50, and 5 minus 50 is negative 45, and 50 minus 50 is 0 again. But if we look at the lowest number, negative 50, all the way to positive 50, that still is a range of 100. We had a range of 100 over there when we added it. So I want you to see, like, our spread is not really changing whether we add it or subtract it. And so that's why even if I'm doing the variance of x1 minus x2, that's you minus your friend or whatever, I am still going to add the variances, x1 plus the variance of x2. And so my formula doesn't change. The square root of 18.03 squared plus 18.03 squared, which is 25.5. My standard deviation is the same whether I add them or subtract them, the independent events. And that has to be one of our assumptions, that the rolls are independent or the plays are independent of each other, which, because we're playing with a die, is an okay assumption to make. And my expected value, the expected value of x1 minus x2 is equal to the expected value of x1 minus the expected value of x2, which is 10 minus 10, which is 0 points. And if we added up all the possibilities, if we did the probability model here, you would end up with 0, because you have an equal number of positive and negative points, and so if you're subtracting, you would get 0.